So today we're going to talk about energy involved in phase changes or heat exchange during phase changes. To do that, we're going to look at a heating curve. And a heating curve is just temperature on the y-axis versus heat absorbed or released along the x-axis. And so as a substance is heated, we can see its temperature rising, but only while it is in a constant state. As soon as we get to a phase change, like the boiling point of water here, we see that the temperature plateaus. And this is going to be because the phase change itself involves an exchange of energy. So a phase change will either release or absorb energy, and that's going to mean that the temperature is not changing. So for example, during melting, the temperature of water will just stay at zero. And that's because the melting process, going from solid to liquid, is endothermic. It takes heat in to do that, and so the temperature is not going to rise even though we're adding heat. And then during the freezing, we're going the other direction from liquid to solid. The freezing process is going to be exothermic. So as we're releasing heat into the environment, the freezing process is going to generate more heat. So rather than getting colder during the freezing process, it'll stay plateaued because of the heat that's being released by the freezing process. So it's exothermic. Boiling and condensing are exactly the same. They're also plateaued. The only difference being during boiling, we're at 100 degrees instead of 0 degrees. So boiling water is endothermic, and so it takes in a bunch of heat. Whereas condensing water is exothermic, and so it releases a bunch of heat. But either way, during those processes, the temperature does not change. If we look at the slopes on this graph, we only have a change in temperature when we have the substance in one physical state. So only have slopes when we have all solid or all liquid or all gas. And so what that represents from 0 to 100 is heat is being added to liquid water and its temperature is rising. The same thing after all of it has boiled away into a gas, then we can start increasing the temperature again, which is why steam can be so dangerous, because boiling water is capped off at 100 degrees. Like we saw that with this specific heat lab. All of your boiling water got to 100 degrees and then it just stayed there. And that's because boiling is endothermic. So as we add heat, it uses it to boil the water. But if you completely boiled a sample of liquid water into gas, then the temperature could start to rise again. If we look at the plateaus, those are our phase changes. So the melting process or the boiling process. You can see much, much greater for boiling generally, and that is because if you think about what's happening, to melt a solid simply means to take those solid particles and make them fluid, make them flow past each other. That takes some input of energy, but boiling liquid into gas means completely separating the particles from each other and overcoming those intermolecular forces such as hydrogen bonds. So when it comes to calculating how much heat in joules is absorbed or released during a phase change, we're going to take advantage of two more numbers that we're going to be adding to our table along with specific heat. We've got heat of fusion, so in this middle column here, measured in joules per gram. It is the amount of heat released as a liquid freezes to a solid, or the heat absorbed as a solid melts into a liquid. Same amount of heat, one is released and one is absorbed. The equation for this is still Q for heat transferred. We still have M for mass. And then we have heat of fusion, which is a constant, which you'll be given. It comes from this table. And again, that's measured in joules per gram. Notice there's no delta T because we're talking about a phase change. And like we've been saying, during a phase change, there is no change in temperature. So as an example, how much heat is exchanged by 25.6 grams of ice as it melts? So obviously we're talking about water that is solid. So the fact that it's solid doesn't really matter because the heat of fusion, of course, is just listed on this table 3 times. It's the same number every time because we're talking about ice becoming a liquid. So Q is going to be equal to 25.6 grams, and then the heat of fusion is a constant. And if you look at the table, 334 joules per gram. So pretty big numbers when we look at heat of fusion compared to our specific heats, which means these phase changes are going to involve pretty big amounts of energy. But if we do 25.6 times 334, of course the grams cancel, and we are left with 8,550 joules. Next, we look at heat of vaporization, which is the last column in our table. And this is the upper plateau. This is the amount of heat released as a gas condenses to a liquid, or if we're going in the other direction and putting in heat to a liquid, causing it to boil and become a gas. Same amount of heat, it's just one direction it's absorbing, and in one direction it's releasing. So for example, if we look at water, the heat of vaporization 2,260. It's quite a bit larger, which makes sense because we're, like we said earlier, we're completely separating the molecules compared to just melting them. So, but that 2,260 joules per gram, that's going to be put in if we're trying to boil a liquid into a gas, and it's going to be released if we're condensing a gas into a liquid. So our equation is the same. The only thing that changes is it's HVAP, or heat of vaporization, instead of heat of fusion. So how much heat is exchanged as 15.6 grams of ethanol condenses? The word condenses means that we are using heat of vaporization, not heat of fusion. Heat of fusion would be going from solid to liquid or liquid to solid, but if there's a gas involved, meaning we've got condensation or boiling, we're going to be using this column here, heat of vaporization. So we're going to say that 15.6 gram mass, and we're going to multiply it by the number from the table for ethanol, which is 879 joules per gram. And of course, grams cancels and leaves us with joules. In this case, 13,700 joules. All right, here's another problem. The cooling tower in a nuclear power plant utilizes the process of water vaporization, so taking liquid to gas, to cool hot pipes from inside the plant. If the heat that must be released is 4.56 megajoules per hour, how many liters of water per hour must be vaporized to keep the pipes cool? So since we're talking about vaporization, we're using our HVAP number, so it's water, so we're going to be using that 2,260 joules per gram somewhere. Now if we think about this, we're solving for mass, because even though the question is asking for liters, we know that with water we can easily go from mass to volume because 1 gram is equal to 1 milliliter. So we rearrange the equation and we get Q over HVAP equals mass. And so if I plug in the numbers, now notice I was given 4.56 megajoules. Now if you remember your Gumu-Ku chart, mega means 10 to the 6th power, or a million of whatever the base unit is. So 4.56 megajoules is 4.56 million joules, or 4.56 times 10 to the 6th. And then on the bottom, I just have my heat of vaporization that we already used once, 2260. So we do the division, and we get about 2,018 grams. But then we still have to take that to liters. So if we think about 1,000 grams is how much a liter weighs, I could have gone from grams to milliliters and then to liters. But if 1 gram equals 1 milliliter, then that means 1,000 grams would be the mass of 1 liter. So, and then rounding for sig figs, we get 2.02 liters. All right, how many milliliters of sweat, assuming the sweat to be the same as water, would cool your body down by 25,000 joules. So again, if we're being asked for volume, then we're going to have to solve for mass. Now again, we're talking about sweat cooling down your body. It does that not by freezing or melting or anything like that. It does that by evaporating from your skin. So this is another vaporization problem. So it's going to be the same equation, same rearrangement, just a different Q value. So 25,000 this time, still dividing by 2260, and this time we get 11 grams, and of course a gram is equal to a milliliter with water, so it's 11 milliliters. Okay, last step here, we have to talk about combining specific heat with phase change. How much heat would be required to raise a 200 milliliter sample of water from 50 degrees Celsius to 125 degrees Celsius? Now, the interesting thing here as we look at our heating curve is we've only dealt to this point with things being, like a liquid warming up but not boiling, or a solid melting, or a liquid boiling, or something like that. But here, we're starting out at 50 degrees Celsius, which is right about here as a liquid, and then we're continuing to add heat until we get to 125 degrees Celsius, so somewhere up here. So this is a little bit different. This is going to involve 3 steps. So first we have to raise the 50 degree water up to 100. Then we have to go ahead and boil that sample of water. So that's going to take a lot of heat. And then we have to take it up some more to 125. So this is actually going to be 3 different problems, and then we're going to add up our 3 answers. So the first step is going to be a Q equals C times M times delta T, because again, this first leg of the problem, the temperature is changing. So you have a delta T, right? And it's liquid water, right? And then from here, it's boiling. So that's going to be a heat of vaporization problem. And then finally, we're going to come back to our specific heat equation, because once it all becomes a gas, it still has to go up another 25 degrees. Because of course, the boiling point of water is 100 degrees, and we're going to 125. So let's look at each step. The first step, Q equals C times M times delta T. It's liquid water at first. So be very careful. The specific heat of the 3 different phases of water are different. They're not the same. So we have to use 4.18 because it's liquid water. 200 grams is going to be our mass for each step, because that doesn't change. The mass of the water, 200 milliliters would be 200 grams. Then we're going to multiply it by 50 degrees. I'm going to be tempted to subtract 125 minus 50 and get 75 and use it there. But don't do that. We're only, for this step, we're only looking at going from 50, which was our starting temperature, up to the boiling point, which is 100. So that's why I'm using 50 degrees Celsius there. I get 41,800 joules. Then we're going to tackle our mass times heat of vaporization. Again, our mass is 200 grams. Our heat of vaporization from the table is 2,260. And that gives me a pretty big amount, 452,000 joules. And then finally, we're going to do one more specific heat problem for the gas. So after it's all boiled, it still has to go up 25 degrees more, but it is now a gas. So its specific heat is no longer going to be 4.18. It's going to be 1.87. And then still 200 grams. And again, 25 degrees Celsius, because it's just going from 100 to 125. And then I get 9,350. And the last step is I'm going to add up my 3 answers. And I get 503,000 joules. So that is taking it all the way from 50 degrees Celsius, boiling all of it, and then taking it up another 25 degrees.